This is Edwards Air Force Base, California. As the dawn of October 14, 1965, brightens the sky to the east, the XB-70 awaits its most formidable challenge to date, flight at Mach 3. XB-70 number 1 is being readied for its first flight at 2,000 miles an hour at an altitude of 70,000 feet. The 6 General Electric YJ-93 engines are fired up, each capable of 30,000 pounds of thrust. Aware of the significance of this mission, the ground crew handles the routine of pre-flight operations with great expectancy. With the ground support equipment disconnected, the XB-70's wheels begin to roll. North American's chief test pilot, Al White, and the XB-70 flight test director, the Air Force's Colonel Joe Cotton, guide the steel and titanium giant toward the takeoff area. At the conclusion of a 260-item checklist, the pilot announces the plane's readiness for takeoff.
5, 4, 3, 2, 1, brake release.
After reaching a speed of 200 miles an hour, the 540,000 pounds of aeronautical equipment lifts from the ground. The XB-70 pierces the sky over a 2,000-mile course, crossing Oregon, Idaho, Utah, Nevada, Arizona, and California. And then, at 10:06 a.m., approximately 1 hour after takeoff, the word came that everyone was waiting for. From 13 miles above Nevada and flying at a speed equivalent to that of a rifle bullet, the plane's instruments register Mach 3.
Oh, there's that big magic number, boy. That's a boy. Congratulations to both of you.
October 14th is an appropriate date for this Mach 3 flight, for it was on this date 18 years ago that Air Force pilot Chuck Yeager first broke the sound barrier. Since that time, a steady progression of speed goals has been met and surpassed. The XB-70 is a leap into an advanced phase of aviation development. Everything about the plane is imaginative and new, but the solid proof of its ability is coming through flight testing. The success of any flight test program depends upon an intricate and well-coordinated network of support equipment, facilities, and talents. In this, the XB-70 is no exception. Edwards Air Force Base is perhaps the most naturally suited flight test center in the world today. In addition to the 15,000 feet of man-made runway, the 12-mile Rogers Dry Lake bed is available for emergency landings. At least a dozen other dry lakes surround the base, each of them capable of handling the aircraft from Edwards Air Force Base. To the north is a 2,000-mile flight test range, providing many alternate landing fields for the XB-70s. At Edwards, the Air Force maintains a constant support capability for its group of contractors. An example of this support is represented by their parachute shop. The XB-70 has a unique deceleration parachute assembly consisting of 3 28-foot nylon canopies, each supported by 32 suspension lines. The triple cluster of chutes in the XB-70 is a first and was specially designed to help break the heavy weight of the metal giant. North American's logistics support site controls over 2 million procured parts, involving some 25,000 line items in this hangar, ensuring the immediate availability of spare parts, supplies, and equipment. Since the beginning of the XB-70 flight test program, this facility has handled over 130,000 transactions. This averages out to about 322 transactions a day. These are 40 by 17.5 lightweight tires, designed to meet XB-70 specifications by the B.F. Goodrich Company. They are constructed of nylon cord and rubber, laminated to a 36-ply rating. The tires are changed after wear has penetrated the top 4 plies. The silver-colored surface is applied to the tires to reflect heat and to keep flight temperatures lower. To detect possible leaks, Air Force personnel apply full pressure of 500 pounds per square inch to the tire for 24-hour storage. If no leaks appear, the tire pressure is released and 100 pounds per square inch of nitrogen gas is introduced to prevent deterioration during storage. Safety features are included all the way through the XB-70 flight test program. To avoid a wide variety of operating problems, guarding against fluid contamination is essential. Each XB-70 contains 280 hydraulically operated devices, such as actuators, motors, and valves. 250 gallons of Oronite fluid is pumped through the plane's hydraulic systems at a maximum rate of 98 gallons per minute. This circulating fluid can reach a temperature as high as 450 degrees Fahrenheit under certain flight conditions. 17 different types of reusable stainless steel filters play a vital role in maintaining the cleanliness of these systems. Systematic replacement is accomplished on all filter elements after a given number of operating hours. Following disassembly of the used unit, its components are washed in a chemical solvent, then bathed in an ultrasonic cleaner. The cleaning treatment is concluded with the elements being heat dried in a vacuum oven. Contamination can be manufactured into the system during assembly, brought in by new fluids, or generated during normal operations. These brass shavings are typical of the contamination that could accumulate in a filter if the cleaning process were not performed. To assure maximum efficiency and trouble-free flight operation from the YJ-93 engines, a regular inspection is performed. In the event of an engine malfunction, the engine is removed to pinpoint the trouble and to correct it. Basic requirements for all Air Force engines demand that inspections be performed after 25 hours of flight time. However, since the YJ-93 is a new engine, this requirement is doubled, and inspections are performed after 12.5 hours. After 35 hours, the engines are returned to the manufacturer at the General Electric Company's Edwards facility for a complete teardown inspection and overhaul. The engine then undergoes a full-duration 1-hour test to be certain it meets all Air Force requirements. The XB-70 is an experimental research aircraft involved in collecting a harvest of flight information. During its development and flight program, the plane has added significantly to the nation's knowledge about the materials, engineering techniques, and manufacturing skills required to build supersonic aircraft of the future. New dimensions to this knowledge are being added almost daily. The National Aeronautics and Space Administration is spending $2 million to provide flight instrumentation, which is supplementing the Air Force's $12 million for the XB-70 instrumentation package. A total of 800 instrumentation parameters can be obtained from Ship 1 during flight, and over 1,000 from Ship 2. Some of the specific test areas under investigation in the current flight test program include research in stability and control, panel response. Microphones are installed in both ships to monitor overall internal noise, skin friction drag, base drag, or suction pressures on the aft surfaces of the aircraft, structural temperatures and thermal environments, landing loads and fatigue, gust loads or atmospheric turbulence loads, acoustic loads, research in boundary layer turbulence, and sonic boom research. These important contributions to supersonic research are gathered and evaluated from the large mass of data generated by each flight of the XB-70 air vehicles. The tape recorder is capable of 92 minutes of operation. During flight, it is possible to obtain 110 million bits of digital data for future processing and cataloging. The data is distributed to other contractors and governmental agencies, such as NASA, the Federal Aviation Agency, and the Air Force. The information is used to verify estimated data for future designs of high-speed military systems and supersonic commercial flight vehicles. Before a typical XB-70 flight plan can be approved, it is essential that many agencies contribute a wealth of information, knowledge, and experience to the project. For example, the weather commander at Edwards Base Operations receives a continual flow of information from 17 different areas along the proposed XB-70 flight route. The information is teletyped to Edwards with readings of the present weather conditions at various sites. Cloud cover formations, air turbulence at different altitudes, and visibility conditions are of the greatest concern to the pilots. The information is relayed to the pilots at a pre-flight briefing.
Starting off from Edwards on the western leg of the flight will be scattered and broken. The base is around 30,000, tops around 35,000. Going into the Boise area, clear to scattered, winds light and variable, around to Cedar City, still scattered to broken. Down into the Edwards area, scattered to broken, bases at 25, tops at 30. The winds at altitude will be light and variable. Temperature at altitude will be a minus 59 degrees centigrade. We should have just a little bit of turbulence in the Tehachapi, China Lake area. Are there any questions?
Here, every phase of the proposed plan is discussed, assuring full coordination of all the flight activities. Still another phase of Edwards' support to the XB-70 flight test program is offered by the RAPCON facility. RAPCON is the radar control system at Edwards. It is a part of a network of 5 Federal Aviation Agency stations, providing air traffic control within the XB-70's normal flight test pattern. The other 4 stations are located at Los Angeles, Oakland, Seattle, and Salt Lake City. An average day at RAPCON can provide service for as many as 200 military and civilian flight operations. Its 100-mile area of authority services such areas as China Lake, Palmdale, and George Air Force Base. As a control station, RAPCON is unique in that the major part of the traffic control is in support of training missions or experimental aircraft test flights. By cooperating with its other agencies, RAPCON offers clearances of civilian and military aircraft along the path the XB-70 intends to fly. As the flight plans are finalized, the physical preparations begin, and the XB-70 is readied for fueling. For this, the Air Force supplies this R1 10,000-gallon tanker. It is the largest vehicle of its type in the world. In the bulk storage area, the tanker is filled with JP6 turbine fuel for transporting to the aircraft. The JP6 is a kerosene-type fuel with a relatively high volatility and good thermal stability. High-performance, high-speed flight vehicles of the future are expected to use fuels with this increased thermal stability. To provide safety during high-speed flights, the fuel tanks are inerted with nitrogen before the fueling starts, and nitrogen gas is mixed with the JP6 fuel by a de-aeration unit. As the XB-70's tanks are filled to the desired point, the nitrogen gas forms a blanket above the fuel, making the ullage space in tanks inert and assuring protection against auto-ignition of the fuel vapors. While on the ground, the XB-70 is entirely dependent upon the ground support equipment, which pumps life through its systems. Basically, this equipment is divided into two categories, electrical and mechanical. Typical of the electrical equipment is this MD4 power unit, which provides the same type power that is generated by the aircraft when it is operating. This enables the plane's subsystems to function on the ground without starting up the engines. North American maintains a complete electrical checkout capability at Edwards. A shielded screen room of copper and lead construction keeps out all outside radio interference. Here, checkout is performed on the plane's communications equipment. Other devices are designed to confirm the accuracy of the plane's subsystems. The brake control unit, air inlet control system, auxiliary gyro platform, data control, navigational system, and various panel instruments are all calibrated in this facility. It is essential that all of the plane's measuring instrumentation perform within specification requirements. The hydraulic ground power unit supplies pressure to the various equipment items throughout the plane, offering assurance the units are operating properly. This unit also provides hydraulic power to start the engines. Air conditioning units are designed to provide cooling for crew and equipment in the forward compartment while the plane is on the ground. Coordinating the various ground support units, a mobile communications command post controls the servicing and ground operations. Currently, there is a list of some 1,250 ground support line items that assist the XB-70 flight test program. For all XB-70 missions, the Air Force provides chase aircraft to perform a variety of supporting jobs. On the day prior to flight, a T-38 takes off to cover the proposed flight range. Its objective is to scout the dry lakes and emergency landing fields, being certain they are fit for emergency use. Hours prior to flight, Air Force personnel load rescue equipment aboard a C-130 aircraft. This equipment is ready for use by jumpers and aeromedical personnel who are airborne during each flight of the XB-70. The C-130 then takes off for the high range, prepared to offer rescue service in the event of an emergency landing or pilot ejection.
Start engine number 2, stand by to start engine number 2. Roger, number 2.
As the checkout of the XB-70 is performed, other aerial support aircraft prepare for the flight. For short-range rescue support, the Air Force provides a helicopter to cover the XB-70's takeoffs and landings.
Mobile comm, data control, the hydraulics disconnected yet?
Negative. Utility is disconnected. Primary, not yet.
Roger.
Momentarily.
Supplementing the normal helicopter personnel, the crew includes a photographer to document the event, a seat capsule expert, and a flight surgeon, all fully equipped to perform emergency service.
We have all GSE removed at this point, and the airplane is just about ready for taxi.
Roger, thank you.
Immediately prior to flight, experienced observers board an F-104 and prepare to accompany the flight for as long as they are able to keep up with the XB-70. Their objective is to offer assurance to the pilots that the mechanical operations of the plane have functioned properly, such operations as the landing gear retracting and the wingtips lowering. From a T-38, a motion picture cameraman provides air-to-air photographic coverage. This film coverage is a normal Air Force requirement for all flights of experimental aircraft. During flight, this control room is the nerve center of the whole operation. Magnetic tapes of all conversations, commands, and responses are recorded for future studies.
All stations just Edwards, XB-70 bound taxiing out.
This is XB-70 ship number 2. In July, the second ship flew for the first time and has now, in 16 flights, progressed to speeds in excess of Mach 2.9.
Go ahead, Frank.
Ready for flutter pulse now.
Roger. Stand by.
Doing them now.
No control cycle, please. And 30 seconds now, coming up on power. Release now.
Engineers familiar with each of the major subsystems watch the development of the flight plan. Constant surveillance is maintained on the air inlet control system, the propulsion units, the chase planes, and the range control. The chase planes act as pacers and offer a calibrated miles per hour speed count. This is a double check on the XB-70's instrumentation. A steady flow of data is telemetered from various sensor points throughout the plane and registered on dynograph recorders. Thermal devices measure temperatures on the plane's skin and engines. Hydraulic pressures, engine vibration, and strain gauge data are also recorded. The real-time benefits of this data permit the flight support engineers to monitor and analyze the most critical parameters throughout the flight, which puts them in a position to advise the crew in the event of an emergency. Thus, the story of the flight unfolds, with the collection of telemetered graphic as well as digital and analog magnetic tape information to form a complete chronological record.
Okay, I got this under 70,000, 292, 532 on the temp, 500 exactly on the airspeed.
During the past 6 months of this report period, the two XB-70 airplanes have flown a series of 31 missions for over 61 hours of flying time. Of this, more than 12 hours was above Mach 2. The two XB-70s are virtually flying laboratories. Every flight represents a tribute to the many people whose coordinated efforts are producing benefits in the form of supersonic research information, applicable to all large, high-speed aircraft of the future.